Welcome to EDU World Space.
Uh, this time we have a new momentum impulse problem where we're given that the starting time t equals to 0 and there's a horizontal force that happens to be in terms of its component vectors 0.280 Newton per second t I hat, that's the horizontal component, plus the vertical component negative 0.450 Newton per second squared, t squared, j hat. So that's the force being applied to a box. Okay, so the force is being applied to a box. Um, we have a box and the force is being applied like that. And then also we're given that the initial momentum happens to be -3. Again, this is given in terms of component vectors, meters per second, I hat, plus 4.00 kilogram meters per second, j hat. So we want to find the momentum of the box, the final momentum at t equals to 2 seconds. So that's what's going on. There's a force that's pushing a box, and yeah, the force is kind of like a variable force dependent on time. You can see that in the formula. We have this variable and that variable, and we want to find, the force is responsible for the momentum. The force is responsible for the change in momentum. And so we want to find, if there's a change in momentum, what's the final momentum at a time of 2 seconds. Uh, so the first thing we're getting is that the impulse at the infinitesimal level happens to be the force which is dependent on time. We can actually call it ft dt. That's our impulse. But you can recall that um, if the force was constant, if the force was constant, then the impulse would be f delta t equals to the change in momentum. Excuse me. And the change in momentum is the final momentum minus initial momentum. So that's what's going to happen if the force is constant. But if it's a variable force, we have to do it differently. So we have to do f dt. You can recall that from previous chapters or previous equations of motion, F equals to ma. That's Newton's second law. But also, according to Newton's second law, uh, acceleration is v final minus v initial over time. So, F, if you bring this t right here, F t is the same as m delta v. At the infinitesimal level, you see that f dt equals to m dv, at the infinitesimal level. Or you can think of the acceleration at the infinitesimal level as the time derivative of velocity. So if you have f equals to the time derivative of velocity times the mass, okay, this mass right here, then you end up with f dt equals to mdv from this equation. So this is going to be helpful in solving the problem, mdv. And so we do know that we could do integrals on this. We could say this is m v final minus v initial f dt. Our goal is to get the final momentum in this problem. So the next thing we're saying is mv final minus mv initial equals to f dt or we could take it from this point. So we could switch it from this point and do it a little bit differently using integrals. So would say something like this. There's some dogs outside. Would say something like this: mdv equals to f dt, and then using integrals, you do that. This is a constant, so you can pull it out. You get the integral dv um, equals to f dt, and this is based on the initial time, which you can call t0 up until t final. If we do the same thing on this one, t0 up until t final, we end up with the initial momentum, which is m v final minus v initial equals to the integral from t0 up until t final of f dt. Okay, and so in the next page, what happens is we want to get the final momentum. Looking back, you can see um, mv final minus mv initial equals to the integral from t0 to t final f dt. Our goal is to get this one, so we say final momentum, we move this to that side, equals to initial momentum plus integral t0 t final f dt. We do have the initial momentum. You can recall from the previous page. The initial momentum happens to be, if you go back, it's here. It is. This is the initial momentum. So it's negative 3.00 kilogram meters per second. I plus, you gotta check again, 4.00 kilogram meters per second j hat, remember the I hat and j hat, plus this part right here, integral from 0 to 2, we're going to 2 seconds. This is the final time, 2 seconds. Then we have to plug in the force, which happens to be 0.280 Newton per second t I hat plus negative 0.450 Newton per second squared. This is t squared j hat dt, because we're doing the integral with respect to time. And then when we simplify this, we get negative 3 kilogram meter per second I hat plus 4.00 kilogram meters per second j hat, and then plus we're going to do the part that's connected to the integral, so we have to do the integral of t. The integral of t happens to be t squared over 2, and so this is 0.280 Newton per second t squared over 2 from 0 to 2, and then plus, we have to highlight that, negative 0.45. We're just going to repeat on the next page because it's a long problem. It's a long problem. So we'll say this is equal to negative 3 0.00 kilogram meters per second I hat plus 4.00 kilogram meters per second J hat plus, now we're doing the integrals. This part, we have to do the integral for this part. It's going from 0 to 2. So 0.280 Newton per second T squared over 2 from 0 to 2, and then plus negative 0.450 Newton per second squared. That's the force itself. And then we do the integral for t squared, which is t cubed over 3. The limits of integration for this one will still be from 0 to 2. It helps us get to the final point of our problem, which is, we have all the momentums now. We have all the momentums. So this is negative 3.00 kilogram meters per second I hat. And the other thing you have to recall is that we did have a I hat on this. So we do have an I hat here, and we have a J hat there. So don't forget the I hat and the J hat. This is going from 0 to 2. Okay, so that has to be clear. And this is also 0 to 2. And so negative 3 kilogram I hat. Just tedious numbers, but you gotta be careful you don't make any mistakes. It helps you, this is what happens in physics, helps you keep track of all the values you're dealing with. So 0.56 kilogram meters per second I hat, and then plus negative 1.2 kilogram meters per second J hat. Connect these two and then connect those two, and so you end up with the final answer of negative 2.44 kilogram meters per second I hat plus 2.8 kilogram meters per second J hat. Hope you enjoyed the problem. This one was the final momentum that you're looking for. This is the final momentum. So again, this is a process. It's similar to some of the stuff we've done before. The only difference is now you're dealing with integrals. You're given a force, and then you're also given an initial momentum. You want to get the impulse of the force in terms of infinitesimal force changes, and that's what's happening right here. Okay, you compare that to the change in momentum at the infinitesimal level, but now we want to deal at the macro level, so we do the integrals on both sides. That's going to make the left side constant in terms of change in momentum and allowing us to integrate the right side in terms of impulse. So these two, this is impulse and this is impulse. The left one is impulse in terms of an already constant mass, and then the right side is impulse in terms of an integral. We plug in the numbers, we move the initial momentum to the right, we do the math, and the final answer is that. Hope you enjoyed the video. Feel free to ask any questions and make sure you have a wonderful day. Okay, thanks. Bye.